Good morning, all my AP Chem students. We are here today trying to talk about, we are actually going to chapter 16 talking about spontaneity. And we have been talking about endothermic and exothermic reactions. And we can talk about that. Let me grab a new sheet of paper here. If we can talk about the burning of methane. We talked about how when you burn methane, all right, when you burn it, you have some oxygen. And if this is the amount of energy that you have in the methane, we have a lot of energy. So think about that gas that we have in our classroom. And then if I go along and I talk about the time factor or the amount of energy that's released as I burn it, if you could recognize that this would be my products. So here's my products. There's not very much energy after I burn all of that methane. Well, this is the first law of thermodynamics that we've been studying, saying that all of the energy is going to remain constant. Even though this has a lot of potential energy and then it's released through exothermic energy after it's being burned, we still remain constant. We can calculate how much energy is here, if it's endothermic or exothermic. Do we have potential energy? Do we have kinetic energy? We've been talking about this in this last chapter, but it doesn't give us a hint as to why the process occurs in a given direction. So that's what we're going to be talking about here in chapter 16. And if you recall, spontaneity is something that, a process that occurs without inside intervention. So as you can see right here that there's no outside intervention and it may occur at any rate or any speed. Well, this is some of the things that we're talking about. If you take a look on page 750, it has some ideas of spontaneity here. For instance, a ball rolls down a hill, but never spontaneously rolls back up the hill. If exposed to air and moisture, steel rusts spontaneously. However, the iron oxide in the rust does not spontaneously change back to iron, metal, and oxygen gas. So you can go ahead and read the rest of those, but it kind of talks about, like the very first one, you can talk about a ball rolls down the hill, but never spontaneously rolls back up the hill. Sure, we can talk about gravity, and we can talk about a few other things with friction and the type of environment that it's rolling down, but really, why does a ball always roll down the hill? So that's what we're going to talk about, and that measurement of randomness is called entropy. So we just called enthalpy, which was delta H. Now we have entropy, which is abbreviated with S. It's a measure of molecular randomness and disorder. Now, a couple examples that you can talk about if you think about your own bedroom. Sometimes it probably has lots of order after your parents have talked to you that you need to clean it up. So you have lots of order, everything has a place. But it takes a lot of energy to put it back into that place. Take a deck of cards, you toss it into the air, the probability of picking it up in the same order, well, let's see, unless we're Ben Jackson in our class, we won't talk about the probability of how he can pick up cards, if any of you have seen any of his amazing tricks. But for the rest of us, that we throw that deck of cards, the probability of picking it up in the same exact order that we tossed it is very, very low. It takes a lot of energy for us to do that. And so the amount of entropy in our universe is increasing, because in nature, as we create that randomness, it's easier, it takes less energy to keep it that way. Now, that's not a reason not to clean your bedroom, but we are creating more randomness, more disorder with more entropy. And in nature, you can kind of take a look at this. If we have low entropy, we probably have more of a solid. Think about the molecules in a solid. They are very tightly packed. They're just moving very, very small. They're basically vibrating. If we have a high state of disorder, then we have a gas. Think about those gas molecules. They're far apart, and they're moving very, very rapidly. And so they have a lot of space. They have a lot of places to go. That is going to create more disorder. And we can talk about the driving force of this is more on probability. So it says entropy is a thermodynamic function that describes the number of arrangements for a given system. So you have some of these diagrams also in your book that we are going to take a look at. So I think you have a picture here on the next slide. Excuse me here, get to the ones that you guys have. All right, so as we take a look at this, we can talk about what's going to happen here if I open this valve. Well, all of us will know that if I open this valve, it makes sense that these gases are going to rush in to this other bulb on the other side. Spontaneously? Absolutely. You open this up and that is going to happen. You don't need any outside intervention. So they want to get to this even possible state. This is what nature wants. It's a lot easier for this to happen, and when this happens, sorry, I'm trying to write down that this is less energy of the system to be in this situation. It's going to take a whole lot of energy to get this back to looking like this. Very, very low probability that that is going to happen. So if you take a look at these possible arrangements, this should make sense to you. All of you are good math students, that we have a chance of 1 in 4 for this particular arrangement of different arrangements. You can see I have 4 here and 0 over here. We can see that the different gas molecules and how they interact in the different arrangements that they have. Well, if we want to talk about the probability of that, we are talking about the increase of entropy. And you can see that again, how that the microstates have given a particular arrangement. What are the possibilities of this happening? As the number of molecules increase, you can see that the probability of finding it in a certain situation is a lot harder. And those are some more pictures of microstates there. But here's what I want you guys to take a look at. If I have one molecule, the probability of finding all of them in the left bulb is 1/2. That makes sense. As I have 2 molecules, you can see how this goes up to 1/4 and 3 all the way down. And if I take a look all the way down here where I have a mole of molecules, this never is really going to occur. How are you ever going to get all of those molecules on the left-hand side? So we're creating more and more entropy in our universe. And again, our driving force is the probability or the spontaneity of whether that's going to happen. So this positional probability is something that we need to talk about. Again, it depends on the number of configurations in the system. So it should make sense to you that solids have the lowest entropy. They're very ordered. The molecules are very close together, and the gases are very, very far apart. Now, if you take a look at page 754, I want you to take a look at these exercises 16.1 and 16.2. Now, as you take a look at 16.1, you can see it wants you to choose the one with the higher positional entropy. What that means is the higher craziness, the more randomness, the more disorder. So for A, are we going to have more disorder with a solid of carbon dioxide gas or gaseous carbon dioxide gas? And you can read that what it says, but there's greater volume in the gases, so there's going to be more disorder. And then the same thing with the other one, we're talking about nitrogen gas at different atmospheres. And that has to do again with our volume. If you take a look at Boyle's law, that we know that Boyle's law is pressure times volume, an inverse relationship, and my pressure is going down, so my volume has to go up. So it's going to be the second situation. Positional probability. Predict the sign of entropy in 16.2 on page 755. Make sure you're taking a look in the book here. It says predict the sign of entropy change for each of the following processes. Solid sugar is added to water to form a solution. Well, they're going to be dispersed, and there's going to be more disorder. You think about that solid sugar, it's in a solid crystal. Then it goes into water. You drop it into water like this. It's like, woohoo, it has all this space to move around in here. There's going to be more disorder. Same thing, iodine vapor condenses. Well, if you're taking something that's a gas like this, and you are condensing it, then the molecules are moving closer and closer and closer together. That's going to create less entropy. So in the top one, you can say that the entropy of delta S is going to increase, a positive sign. For this one, it's going to be negative because you're creating more order. So that's basically this section. So 16.2 we'll talk in the next discussion. So you just need to understand that entropy is abbreviated with S, and it increases, and that does not remain constant in our universe. We are creating more and more entropy all the time as our world continues to evolve. All right, have an awesome night, and I'll see you later.